Welcome to Online Precalculus. Today, we're going to cover sections P2, which is exponents and scientific notation. So the objectives for this section are to use the properties of exponents, to simplify exponential expressions, and finally to use scientific notation, and then we'll do some word problems, some application problems using scientific notation, big numbers. So first, we have to sort of remember all the properties of exponents, okay? And there are quite a few of them. So if we look at these as we go down, the first one is the negative exponent rule. And that means that if b is any real number other than 0 and n is a natural number, so that's the exponent, if it's a natural number, and we have b to a negative exponent power, we take the expression and we move it to the bottom of a fraction, and the expression becomes 1 over b. So if we look at our examples, 5 to the negative 3 becomes 1 over 5 to the third, which is 1 over 125. The opposite is also true, which means that if we have 1 over b to the negative n power, that is equal to b to the n power. Because, right, if you can see from the example, it turns into 1 over 4 to the positive 2 power, which then turns into just, right, divide a number by a fraction, you multiply it by its reciprocal, and we just get the 4 to be in the numerator. So basically, what this says is that if we have a negative exponent in the numerator, by moving it to the denominator, it becomes positive. If we have a negative exponent in the denominator, by moving it to the numerator, we can make that exponent positive. Okay. Next, we have something called the zero exponent rule. And that says that if b is a real number other than 0, anything to the 0 power is 1. Anything to the 0 power is 1. Be careful with an expression like that, because if you remember order of operations, only the 5 is attached to the 0. Unlike in this expression, the whole negative 5 is raised to the 0 power, you get 1. Here we do the exponents first, and then the multiplication. So it's kind of like something like that. Okay, so the exponent comes first, and then we multiply it by the negative to give me negative 1. Okay. But any expression in parentheses that is raised to the 0 power becomes 1. Okay. Next, we have something called the product rule. So if b is a real number or an algebraic expression, and m and n, the exponents there, are integers, okay, all we have to do is same base, exponents, we combine and add the exponents together, as long as the bases are the same. So we add the exponents, use the sum as the exponent of the common base. So then these two would get put together, and it would be b to the m plus n power. So in our example, 2 squared, 2 to the third becomes 2 to the fifth. That works with negative exponents as well. X to the negative 3 power times x to the 7th becomes x to the positive 4th. The power rule. So this is a power to a power. So if b is a real number or algebraic expression and m and n are integers, power to a power, b to the m to the nth power becomes b to the m times n. So same base, where we're multiplying those two bases together, you add, but if we have a power to a power, we have to multiply the exponents together. So 2 times 2 squared to the third power gives me 2 to the 6th power. Works with negative exponents again as well. So x to the negative 3 times 4 gives me x to the negative 12th power. And then we have to use my first rule. Okay, so we can combine these properties together in order to simplify my expressions. So the quotient rule. So now, instead of having a product like we have up at the top there, we now have a quotient. And now instead of adding the exponents together, we subtract them. Okay, so there's a couple ways to think about this, and it's up to you which way really is going to work for you. But what I like to do is You can always do this method right here. Take the top minus the bottom. If it's positive, you leave it where it is. If it's negative, you're going to have to move it later. What I like to do is just look at which exponent is bigger. So here we have 2 to the 8th, 2 to the 4th. 2 to the 8th is bigger. When I subtract them, right, 4 of these on the bottom are going to cancel with 4 of these up top to give me 2 to the 4th. However, in the second example, right, the 7 is on the bottom. There are more x's on the bottom than there are on the top. So you can think about it like this. X to the third means x times x times x over 1, 2, 3, 4, 5, 6, x to the 7th. So 3 of these are going to cancel, and we're left with x to the 4th on the bottom. So you could do this method, just subtract the top and the bottom. It always will work, right? 3 minus 7 gives you x to the negative 4, and then you have to just move it to the bottom. What I like to do is just pick the bigger number. All right, 7 is bigger, so I go 7 minus the 3, and then because the place I started with, because the x to the 7th is on the bottom, my answer is going to be on the bottom as well, and it will be positive. So either way that you want to think about that is fine, but I tend to just use the canceling method instead of the subtraction method, but either way works. Product to a power. This basically says that if you have two things inside of a parenthesis, they both get raised to that exponent. So in here we have a -2 and a y. So -2 gets raised to the 4th power, the y gets raised to the 4th power. Remember that -2 to the 4th power becomes positive 16. Same thing when there's 3 things inside. Works with quotients as well. So quotients to a power, both terms inside of the fraction get raised to the exponent. I'm going to add something to that as well and say that if we have something like this, but let's raise it to the -n power. Let's watch what happens, and then we'll make a rule for that. From the example above, we know that both of the a and b have to get raised to the -n power. So that's a to the -n, b to the -n. Well, if I have a negative exponent, I have to move it to the bottom of a fraction, and if it gets positive. And if I have a negative exponent on the bottom, it moves to the top and becomes positive. And I can sort of recall that, well, if I did this, if I did the first step, both things inside the parentheses got raised to the -n, I can sort of factor out that exponent, and I can say that, whoops, b over a would be to the positive n power. So this is my new trick, is that if I have a fraction raised to a negative exponent, I can flip that fraction and make that exponent positive. Okay? But in either case, everything inside the fraction, including a negative sign, and there's only one negative sign there, and usually if we have a negative sign, we assign it to the thing in the top and the thing in the numerator, especially if it's a number. That's way easier to deal with than a variable with the negative there. And then once I finish the problem, I can put it back out front, right? Just don't think that there's two negatives there, because there's not. All right, so that was all the rules. To recap, we have negative exponents go to the bottom, 0 exponents turn things into 1, same base, add the exponents together, power to a power, multiply the exponents, same base with division, you subtract the exponents or cancel. Anything in parentheses all gets raised to a power, and anything in parentheses with division gets raised to that power as well. Okay. So what are we going to do with all this? Okay. So we are going to try to simplify exponential expressions. And the trick to remember here is that we have to remember when we're done, right? We have to realize that when we simplify these expressions, eventually we're going to be done, and we have to be able to recognize that. So how do we know when we're simplified? No parentheses, no powers are raised to other powers, each base occurs only once for now, and no negative or 0 exponents. I say that each base occurs only once because eventually we might have to rationalize the denominator if we have fractional exponents, but we're not there yet. Okay? So some examples here on simplifying exponential expressions. So we can first remove the parentheses by using my product to a power or quotient to a power rule. Simplify powers by multiplication. Put bases together with adding the exponents or subtracting the exponents, and move negative exponents to the numerator or to the denominator, depending on whether they started in the top or the bottom. Okay. So again, remember my goal. No parentheses, no powers to powers, each base once, no negative or zero exponents. Okay. So let's try to simplify a few exponential expressions. Okay, let's start with part A. Okay, so inside the parentheses, I notice a number, x and y, so there's nothing I can put together to make this a little bit easier to start with, but everything is raised to the third power, so I am going to take -3 and raise it to the third power, x to the fourth, raise it to the third power, and y to the fifth and raise it to the third power. Everything inside the parenthesis gets raised to the third power. -3 to the third power means -3 times -3 times -3, which is -27. Power to a power, we multiply the exponents together. That gives me x to the 12th power and y to the 15th. Okay, now I ask myself, is this simplified? Okay, there are no parentheses. There are no powers to power anymore. Each base occurs once. I got a number, -27. I got an x, I got a y. And no, it's okay to have a negative number, but no negative exponents or zero exponents occur. So that means that that is as simple as I can make it. All right, to part B. Okay. So we have this expression. Let's just multiply all the pieces together. Right, let's start with the numbers. So we can use the commutative property. We can multiply these in any order I want. I'm just going to write it out so we're very clear what's going on. We take the -7, we multiply it by the -2. I take the x and I multiply it by x to the 5th. And I take the y to the 4th, and I'm going to multiply that by y to the 6th. Right? And that's all I'm doing here, is I'm just putting the same stuff together. That turns into a +14 x first power and fifth power. I would add those exponents together, and I would add the exponents of the y together as well. So I would get +14 x to the 6th. Again, that is simplified, and I know by going through all my rules. Okay. For part C, we can now start using division. Okay, and we can divide -35 over a +5, and we get a -7. Now, where's that -7 going to go? Is it going to go in the top, or is it going to go in the bottom? Well, 35 over 5 is 7, as opposed to 5 over 35 would be 1 over 7. So -7 is going to go in the numerator. Let's just put a fraction bar just like that. Okay? And then at the end, we can move the negative to the front. All right, so here's what I'm talking about here. X squared to x to the 6. X squared over x to the 6. I could subtract them and get x to the -4th and then move it down later, or I could just say 2 of these cancel with 2 of these in the bottom, and I get x to the 4th on the bottom. Now, to make this easier, I'm going to move the y to the 8th power to the top and then combine them both to get my final answer of y to the 12th over x to the 4th. Okay? And again, the negative can go in front of the 7. It can go in the front like that, just as bad form to leave it in the bottom. Okay? Here's an example to use my bonus rule that I worked out before. In that I have a negative exponent, I have a fraction with a negative exponent. If I flip the fraction, if I keep everything inside the fraction exactly the way I see it, just change the numerator and the denominator, it makes the exponent on the outside positive. And this makes the calculation a little bit easier, because now when I raise everything, 4 to the 3rd power is 4 times 4 times 4, which is 64. X power to a power, we multiply the exponents, x to the 6th. Now, nothing is negative. I have no negative exponents, which I would have if I hadn't done the first step. So I can just, it's simplified, it's done without having to do anything else. Let's do a few more of those. Let's do the checkpoint problems. Okay. So part A, raise everything to the 4th power. 2 to the 4th would be 2 times 2 times 2 times 2, which is 16. So that would be 16 x power to a power, we multiply, y power to a power, we multiply, and get 24. Okay. Part B, we are just going to multiply those two terms together. So we have negative 6 times 3 gives me negative 18. I have x squared and x. That gives me x to the 3rd. Y to the 5th and y to the 3rd gives me y to the 8th power. For part C, 100 over 20 gives me 5, which would be in the numerator. I'm not sure if I need a denominator yet, but I'm just guessing. Well, yeah, I am, because I look at this. So there's more at the bottom here. 16 minus 12 gives me x to the 4th. 16 minus 12 is 4. And because the 16 was on the bottom, the 4 goes on the bottom as well. I can move the y to the 4th up to the top and combine those together to give me y to the 6th. And finally, part D, again, I'm going to use my trick and turn this around. Actually, let's do it without that. This becomes 5 to the negative 2, x to the negative 2, and y to the negative power to a power multiply 8. And then from here, I just have to move them all around, right? Negative exponent goes to the bottom, becomes 5 squared in the bottom, which is 25, or 1 over 25, right? X squared goes to the bottom, and y to the 8th goes to the top. So again, I kind of feel like flipping it and making the exponent outside positive is a little bit easier, but it definitely depends on the problem. Okay. Simplifying exponential expressions involves a lot of steps. Are there common errors that you can avoid along the way? Yes, of course there is, and the textbook here has the list of the column errors. So the first column has the correct simplification. The second column is the common error to avoid. Okay. So first, the correct thing to do is to add the exponents together, right? Same base, add the exponent. You know, it's typical to some people sometimes to forget that and multiply. For the next one, again, same base, you add the exponents together. The base does not change. Okay, you don't multiply the 3's together. 3 squared is 9 times 81, right? It doesn't mean it's going to be 9 to the 6th power, right? It's going to be 3 to the 6th power. It's 3 times 3 twice, and then 3 4 times, so now it's 3 6 times. For this one, right, we're going to subtract the exponents, not divide them, right? It's not 5 to the 4th power. Here, in the fourth example here, both of them get raised to the 3rd power correctly. Here, the 4 is not cubed. This is the correct way to move a negative exponent to the denominator. It has nothing to do with the sign of the expression. It only changes the sign of the exponent. Okay? And then this is one term, all moved to the bottom of an expression, not whatever this just happened here. That is something very, very different, right? We're now splitting it into two terms where it is two terms inside of the parentheses, but the entire term should be moved to a bottom of a fraction. Okay? So just be careful with those common mistakes and try not to make them. Okay? So let's talk a little bit now about scientific notation. All right? Scientific notation is basically a way of easily writing large numbers. So as of December 2011, the national debt of the United States was about 15.2 trillion. Currently, it's much more. I had it up on my screen. Oh yeah, there it is. It is currently 26 trillion, 26.7. So it has gotten a lot bigger over time. Okay, so this amount of money the government had to borrow over the years, mostly by selling bonds, because it spent more than collected in taxes. A stack of $1 bills equaling the national debt would measure more than 950,000 miles, so much more today. That's 2 round trips from the Earth to the Moon. Because a trillion is 10 to the 12th power, we can express that a little bit easier with scientific notation. Okay. Normally with scientific notation, right, we because 1.5 or 15.2 is equal to 1.52 times 10, we can express the national debt in scientific notation with one more power of 10 there, and 1.52 times 10 to the 15th to the 13th. So scientific notation, what is scientific notation? It is a number that is expressed between 1 and 10 times a power of 10. So it's a times 10 to the nth power, where the absolute value of a is greater than or equal to 1 and less than 10, and n is an integer. So this number has to be, it can be positive, it can be negative, but it's going to be between 1 and 10. Its absolute value is going to be equal to 1 or less than 10. And n is going to be an integer, which means it could be positive, it could be negative, but it is not going to be a fraction. And pretty much the only time we are going to use the x symbol to represent multiplication is with scientific notation. Other than that, we really don't use it, maybe except for things like cross product, but we're not going to get to that for a while. Here's some, in case you didn't know, now you know. The names of large numbers. So we should pretty much be familiar with 100,000, million, billion, and trillion. After trillion, after 10 trillion, 100 trillion, when we get to 1,000, we call it quadrillion, then quintillion, sextillion, septillion, octillion, and then nonillion as 10 to the 30th power. Google, not the search engine, it's Google, right? Spelled a little bit differently, but this is where the name came from, is 10 to the 100th power. And then the 10 to the Google power is something called a Googleplex, which is actually the name of Google's corporate headquarters in Mountain View, California, Googleplex. Okay, so, interesting trivia there. So, how do you convert from scientific to decimal notation? Here are 2 examples of numbers in scientific notation, right? 6.4 times 10 to the 5th means 640,000. And 2.17 times 10 to the negative 3rd means, 0.00217. And we see that the number with the positive exponent is pretty big, and the number with the next exponent is pretty small. And you can use the exponent to change a number in scientific notation to decimal notation. If the exponent is positive, move the decimal point to the right. If it is negative, move the decimal point to the left, depending on the exponent. So, if we have a number like 6.2 times 10 to the 7th, we are going to take this decimal and we are going to move it to the right 7 spots. So that's 1, 2, 3, 4, 5, 6, 7. And then I just put a comma every third one to help see how big this number is. And it is 62 million. With a negative in the front, doesn't change it, right? We just make negative, right? 1, 2, 3, 4, 5, 6, 7. So this one becomes negative 62 million. The exponent is the same, right? It's still times 10 to the 7th. Just one's positive, one's negative. Same thing with these two. Both of them are the same, right? Except now we move the decimal 3 times to the left. So that becomes 0.123 and then we have to move it there. So 3, 019. And here is the same thing, except negative in the front. You could just put the decimal point. You could just put a leading decimal point. I tend to do that sometimes, like putting like 0.002. You could put that. It is good habit to get into to put a 0 point there, but you know, depends what kind of mood you're in. Let's do one more with our checkpoint, and we have negative 2.6. So it's negative 2, right? This is the first move. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I go back, and every 3 I put a comma so I can see that it is a negative $1 trillion. Here, I like to start like this, right like that. And I go 1, 2, 3, 4, 5, and then this is the last move, so that's 6. 017, those are already behind the decimal, and that is my number. Very, 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 very small. So the opposite is also true. So convert from decimal to scientific notation. We reverse this procedure. So first, you determine the numerical factor, and then move the decimal point the given number to obtain an absolute value between 1 and 10. And then determine the exponent. The absolute value of n is the number of places the decimal point was moved. Doesn't matter left or right. Okay, if it's left, if we're moving the decimal point to the left, it'll be negative. If it's right, we'll get a sorry. If we're moving the decimal point from where it's starting left, then we're going to get a positive number, and if we're going to move it to the right, then we're going to get a negative number, right? Because we're going to reverse the process. So this is what I mean. Here's the decimal point now. So now when I shift it back this way, this is a big number. It's going to have a positive scientific notation or scientific positive exponent. This is no good, right? We can't have 34, right? So we have to have 3 point, and then I need every number that's left over. So 4, 9, 7. The rest are zeros. So I can get times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And that's my exponent. That's my expression in scientific notation. Same number again with a negative in the front. You just put a negative in the front. It does not affect anything else in the problem except the negative in the front. So now I see that I have two very, very, very small numbers. So I'm going to move this decimal point to the right and until I get a number between 1 and 10. So that would be 8.02 times 10, and it's going to be a negative exponent. What's that negative exponent going to be? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then this one would be negative 8.02 times 10 to the negative 11th power. Okay, and a little checkpoint. Same thing. Again, we see big number, 5.21 times 10. It's going to be positive. 1, 2, 3, 4, 5, 6, 7, 8, 9. And negative 0.6893 times 10. And this is a small number. This is a period, not part of the problem. 1, 2, 3, 4, 5, 6, 7, 8. Okay, times 10 to the negative 8. All right, let's do a couple problems dealing with scientific notation. Okay, and we're going to run through these. Right, I do too many of the checkpoints from here on, but mostly these are pretty straightforward. As of December 2011, the population in the United States was 312 million. Express this population in scientific notation. Well, that's 312 million, so that's times 10 to the 6th power, because that's what a million is. But that is not the right way to write scientific notation. I need to change this to a number between 1 and 10. Okay, that means that I need to move this decimal 2 more that way, which means I need to add 2 to the exponent. Okay. Again, we'll do the checkpoint real quick. 410 is not in scientific notation. So this becomes 4, and I don't need the 0 there, right? It can just be 4.1 times 10. But if I move the decimal 2 more times that way, I have to add 2 to the exponent, right? Because I'm starting with 4 instead of 410, I need to multiply by another 100 in order to get the same answer. So properties of exponents can be used to perform computations with numbers that are expressed in scientific notation. Okay, so this is why scientific notation kind of went in with the with this section that dealt with the rules of exponents. Because yes, we could just plug that problem into a calculator, and we're probably going to use a calculator anyway. But you can do this. You can do a little trick to this. We can multiply these two numbers together and get 4 times 6.1 to be 24.4. And then when I multiply those two together, I can just add the exponents together. So it becomes 10 to the negative fourth. Okay. Now that's not in scientific notation, so I'm going to move the decimal point 1 that way. So that's 2.44 times 10. And because I move it to the left, I have to add 1 to the exponent. And so that gives me 10 to the negative 3. All right? Because if I move it to the left, right, to put it back to my answer, I have to multiply it by 10 again. I need another 10. I need 1 less negative 10. Okay? And division works the same way. So you can take the 1.8 divided by 3 and get a 0.6. So this would be 0.6 or 0.6 times 10, 10 to the fourth over negative 2 gives me 10 squared. 0.6 is not between 1 and 10. So now when I move the exponent that way, I can take, sorry, little mistake here. 4 minus negative 2 is 10 to the 6th. There we go. Sorry about that. And right, the negative 2 comes up, becomes positive 2, combines with the 10 to the 4th to give me 10 to the positive 6th. And then when I move the decimal 1 point to the right, this becomes 1 lower, which is 10 to the 5th. Well, let's try another 2 since I messed that one up. Okay, so yeah, good. B's pretty much the same. So 7.1 times 5 gives me 35.5 times 10. Add these two together to the negative 2. When I move this to the left, I get 3.55. Adding 1 gives me 10 to the negative 1 power. 1.2 divided by 3 gives me 0.4 times 10 to the 9th power, right? 6 minus negative 3, or negative 3 up to the top becomes 10 to the 6th times 10 to the 3rd, which is 10 to the 9th. Move this 1 to the right, so it's 4 times 10 to the 8th power. Some applications, okay? So here's a nice word problem. So here's back to our national debt, tax cuts and spending increases. We began accumulating large deficit in the 80s, and in order to finance, in order to pay for things, right, we had to borrow money. So as of December 2011, this is $15.2 trillion. So here's a nice graph of what happened to the national debt over time from 1980 to 2011. Again, like I mentioned before, it is much larger now. So example 6 on the next page is going to show us how we can use scientific notation to calculate things with this. Okay, so we have 15.2 times 10 to the 12th trillion dollars. At that time, the U.S. population was approximately another number we just used before, 312 million. If the debt was evenly divided among every individual in the United States, not taxpayers, just every person, how much would each have to pay? So that's division, right? So if we want to know, we have the whole, everything, we divide it by the number of people, that's how much they have to pay. And then we can use the technique that we just talked about, 10 to the 8th, of dividing and using our rules of exponents. So we take 15.2 divided by 3.12 gives me 4.87 times 10, 12 over 8 to the 4th. Well, what kind of number is that? So that's 4, 1, 2, 3, 4. So it's $48,000, $49,000. So that means that in 2011, if everyone were to pay off the national debt, it would be $48,000 per person. Well, unfortunately, currently there are more people in the United States, but our debt is also much higher. So currently the debt per citizen, per every person, is actually 81,074. Right, so it's $81,000. So a lot of money. Hopefully someday we'll pay it off. You know, numbers like this, numbers like the national debt with really, really big numbers are pretty typical applications of scientific notation. Okay, numbers that are really, really big, that deal with big things, it's easier to use scientific notation. Another idea is black holes, like where things in space have very, very big numbers or very, very small numbers. So what is a black hole? Right, a region of space where matter appears to vanish. Scientists theorize that when massive stars run out of nuclear fuel, they begin to collapse under the force of their own gravity. And there's a model called the Schwarzschild formula that describes the critical value to which a radius of a massive body must be reduced for it to become a black hole. Great. You've probably never heard of this before, but guess what it's going to use? It's going to use really, really small numbers and really, really big numbers in scientific notation in order for us to run the calculation. So here's the formula. Here's all our things that we know. What length the radius of the sun must be reduced to for it to become a black hole. And if the sun's mass is 2 times, and again, a really big number, 2 times 10 to the 30th kilograms. So basically, we know all the stuff, right? We know 2, we know G, we know M, and we know C. So all we got to do is plug these numbers in and run the calculation. So let's write the formula again right here, that R sub S is equal to 2GM over C squared. Okay, so that's going to be 2. G was 6.7 times 10 to the negative 11th. And this is all multiplication, so it's not like we have to distribute any of this. So, you know, this is all one big term. And then M was, from right here, 2 times 10 to the 30th over 3 times 10 to the 8th squared. Okay, again, we don't need distribution because these are not, there's no addition here. This is all one term. So I can just pick and choose what I want to multiply by. And so on the top, I'm going to take the 2, the 6.7, and the 2. So that becomes 4 times 6.7 to give me 26.8 times 10 to the 19th power, right? Negative 11 plus 30 over, now I have to square it, so it becomes 9. I square both things inside the parentheses, power to a power. I multiply the exponents together. Now I can divide 26.8 divided by 9 would give me 2.97 times 10 to the third, which is 2970 approximately, right? And I rounded this a little bit. Actually, this should be another, this is 7 repeating, so that should be an 8 and an 8. Okay. Interesting stuff using scientific notation, but I believe that is the end of this section, and that is section P.2 Exponents and Scientific Notation.